Thanks to James Webb, we are now analyzing the atmospheres of other planets. And we've seen a lot of exciting news, like the potential biosignature at K2-18b, and other kinds of chemicals in the atmospheres of other planets. And it feels like we are progressing to this time when we will start to know whether or not there are other planets with life here in the universe. But James Webb is the very first, simplest version of this capability, that there are other bigger telescopes, interferometers, ground-based telescopes that will be working on this problem as well. And we may get to this place where we have analyzed the atmospheres of 30 planets, 50 planets in a ever-widening sphere around us here in the Milky Way. And the question is going to start to rise, which is, are we alone? As we examine world after world and we fail to find any biosignatures in the atmosphere of that planet, what does that tell us about how common life is in the universe? We're all expecting that eventually we will find the presence of life on that other world. But what if we don't? My guest today is Dr. Daniel Angerhausen. He's a senior scientist at ETH Zurich, and he's an affiliated scientist with the SETI Institute. He is one of the minds behind the LIFE telescope, the Large Interferometer for Exoplanets. This is a constellation of spacecraft that would fly in formation. They would use a special technique called nulling interferometry to be able to examine the atmosphere of another planet, to block the light from the star and tell us, with the best technology that we have, to find out if there's life on that planet. And the expectation is that we will find life. But in a recent paper, Daniel asked the question, what if we fail to find life? What does that tell us about how much life there is out there in the cosmos? All right, enjoy this interview with Dr. Daniel Angerhausen. Daniel, we've talked before, and now I've got you back because you posted a new paper about our chances of being able to find life out there in the universe. And, a lot of times people say, we're searching for life and, we can never know. You can't prove a negative that, as we don't know if there's life in the universe until we've checked under every single rock in the entire observable universe. But you, in your new paper, you propose that there is a way that we can start to statistically understand just how prevalent life is in the cosmos. Can you help us understand this?
Yes. So I think we talked about this last time already. So I'm always trying to approach this whole question of life in space along these lines from Arthur C. Clarke. So either we are alone in the universe or we are not. And both answers are similarly terrifying, I think he wrote. So I'm also approaching the whole problem trying to be as unbiased as possible. So there's colleagues in the community who claim life started so early on Earth that it's totally abundant and everywhere, and then there's other people who have this rare Earth theory that is like just a coincidence after coincidence after coincidence that created life, and certainly intelligent life. So I wanted to find out, if we build these future telescopes that scan our neighborhood for potential planets that are habitable and potential biosignatures, what would we learn if we don't find anything? Because on the one hand, this is something we need. If we argue that we want to build these missions, we have to make sure that even the null results gives us some insight on nature or the nature of life itself. So this is the question we started from. So what if we find nothing, which is actually the title of the paper, right?
Right. Yes. And I mean, where we stand today, it's sort of interesting timing because obviously everyone is talking about this discovery of potential biosignatures at K2-18b. Others are quite skeptical that either the detection has been made at the level of significance that it's been claimed, but also that a biology is the only way that you can get these chemicals. We find these in interstellar space. We find them in asteroids. Like, there are ways that you can get dimethyl sulfide and dimethyl disulfide and not have it being caused by bacteria. But that is the way we find it here on Earth anyway. And so I think first, it's going to be tricky to just know whether or not you have made a conclusive detection of some kind of biosignature on one of these worlds. So let's start there.
Mm-hmm. Yeah, so this is actually something we included in our study in like the second step. I think the first step was assuming we are perfect observers, right? We look at a planet, and then after this observation, we can, with 100% certainty, which is, not possible in science anyway, but just for the sake of this study or this first order estimate, we assume we look at the planet, and after that observation, we know with 100% accuracy there's life or not, right? So, and then it's basically a coin flip, right? We look at all the coins in our neighborhood, and then see which fraction of coins show heads or life in that sense. So this is a relatively easy, let's say, coin flip experiment or statistical experiment. But then as soon as you get into this, but we don't know this perfect answer all the time, right? We might only have like an 80% accuracy that we found live. And what does that mean anyways, right? If someone says I'm 80% sure I found life, what does that mean? Are they wrong 20%? Or so this is all what we try to also um parameterize or find a metric for our not knowing, and also include that in the statistics. And then also, if you go a step farther, that then also means we have to probably ask better questions. So we probably can't we can't answer the question, is there life on this planet or not, but we can answer the question, is there oxygen and methane above a certain level, is the temperature in the right regime. So this is also part of this study. So yeah.
And I mean, this is an ongoing work in the astrobiology community to even settle on what is a definition of life. And I mean, right now, there doesn't seem to be any single molecule that would say, okay, we found life. You say oxygen, methane, any of these. The next strategy is maybe it's about the interplay of these molecules that you watch as methane increases, decreases over some kind of seasonal cycle. Do you feel confident that I mean, with that first phase that you mentioned, okay, we know that we've done a good job of detecting the chemicals in this atmosphere. Okay, great. That feels like it's a solvable problem. The second one, do you feel like the astrobiology community will get to a place where they think they have what is an acceptable biosignature that they can feel confident is actually life?
Okay,
Ever?
not too untangle here. So I think, first of all, I think there are some real smoking gun biosignatures, which are actual technosignatures. So I think
Yes.
we talked about this before. So if you found like CFCs or some industrially produced molecules which can only be industrially produced in an atmosphere, then this is pretty much the smoking gun for advanced life, right? So I think, at least on that hand, they might be rare or not even there, but these technosignatures by themselves are pretty unambiguous. But then if you come, as you said, to these, more biological molecules, there's most of the time also some sort of geological process, or maybe formation process, or some photochemistry that abiotically produces these molecules, but not necessarily in these amounts to change atmospheres on a global scale. So then we have to think again, if you have a biosphere, how much biomass do you have? Does that biomass have enough metabolism to produce these huge amounts of this thing? So this is where, we have to juggle between geologists and volcanologists and people who work on photochemistry to compare what the biologists tell us, comes out of these. And then ultimately, it's actually also a philosophical question. So there's always the unknown unknowns. So there was an interesting paper about these unconceived alternatives. So even if we explore all the human knowledge on geology, there might be still a geological process we never thought about produces these. So this is really where this interface of astrobiology and philosophy comes into play. Can we parameterize our non-knowing of something? And this is also something we try to include in the study, at least if we assume we can at least put a number on this not knowing at some point.
And I mean, obviously, people will always say, you're just trying to search for life as we know it, that Earth life has these various chemical inputs and outputs, and we know that planet Earth, as you say, has these geological cycles, and so we're trying to map what Earth looks like onto some other world. How can we be so arrogant to assume that life is going to be anything like what we are? Maybe they used boron as a chemical and so on, and that the inputs and the outputs are going to look totally different. And I think that's a perfectly valid concern, and that how do we imagine the unlimited possibilities of the ways that life could could go. But I think that is a solvable problem as well. At some point, you're looking for imbalances in the chemistry of an atmosphere.
Exactly. So I think these are like two approaches. I think it's legitimate to start with Earth just as, the benchmark, as that one planet that we know has life, and then also as some sort of a sanity check. This is how we started for the Life Telescope, for example. We modeled an Earth at 10 parsec and asked ourselves, would we, almost like this Carl Sagan looking back at Earth experiment, but just a bit farther away, would we even identify ourselves? And this is very the first sanity check. So we should be able to find ourselves. And then you slowly but surely move the signpost from there. So you look at certain extreme environments, abiotic swamps that produce a lot of methylated chlorides, or you go to the phosphine, which is under certain circumstances a biogenic gas, and then see what happens if you have a biosphere that's full of these microbes that produce it, and then you get to some other potential biosignatures, and then eventually you become completely agnostic and really look for what you said, just anomalies, stuff out of equilibrium, stuff that can't be explained just by geological processes. So I think there's room for all of this, but really if we just put all of these approaches together, so the super agnostic approach and the super targeted Earth twin approach, then we can build the right missions to really find all of the spectrum of potential life out there.
Okay, so we're in this future, this bold future, where the astrobiologists have got some kind of agnostic diagnosis of planetary atmospheres, that they say, okay, if we see planets doing this, we can feel confident that this is life. And so then you begin the search using this new diagnosis, and as you expand your search and as you fail to find life on any of the worlds, what are the various factors that you're going to be taking into account at this point?
So first order, it's really just the number of planets we observe. So if you observe 10 planets, 20 planets, 50 planets, and intuitively, the more we observe, the lower we can push the upper limit. So this is where it really is a coin flip experiment. So if you want to look for the fraction of planets that have life, let's put the definition to aside for a second. Then, if we observe 50 of them and don't find any life, we are 99.9% sure that the fraction of planets with life is lower than, let's say, 10%. And then if it's just 25 planets we observe, the upper limit can only be 20%, but at least we get a pretty good estimate of the upper limit. But then the next step is, what if each of these individual observations we just are 80% sure, right? So if I do 50 observations, and for each of the 50 observations I'm just 80% sure, and again, we have to find a framework how to arrive at this 80%, but let's assume we agree on we are 80% sure for, then of course this decreases my ability to push an upper limit. Then the upper limit is a bit higher because we have to include this uncertainty for each individual observation. So in this way, it comes back to ask the right questions. So we should ask questions that we can answer for each of these individual planets with the best significance or best accuracy that's possible. So that's by asking, is there life? Maybe not the best question to ask, but a more specific question for a certain molecule. And then you can derive the fraction of planets who have oxygen, for example, or something like this.
And I mean, this is, you mentioned it's the planets that we observe. So we're not necessarily observing in this comprehensive way in a sphere around the Earth, and that is expanding. We're looking at the best possible targets that we're able to find, whether they're lined up so that we're seeing them in the transit, or the brightness of the planet compared to the brightness of the star fits within the capabilities. So does that cause some kind of bias?
It very probably does. So there's also works. So for example, with these future telescopes, or this next generation of telescopes, we really just start to analyze our neighborhood. So let's say, maybe 100 light years, 150 light years around us. So really a tiny little bubble around us in comparison to the whole galaxy. And there's already work on people who say that this there's galactic habitability, for example. So if you're farther out in the galaxy, you might be lacking the metallicity, and if you're too close to the galactic center, there might be too much radiation from the black hole in the center of the galaxy. So we are really just, whatever number we derive is just the number for our neighborhood. So it's probably not like a number that you can immediately extrapolate to the whole galaxy or the whole universe, but at least it's, in places that are similar to this, arm of the galaxy that we live in. This is the number for, or upper limit for potentially habitable or inhabited planets. Yeah.
I mean, where we live here in the Milky Way, we are surrounded by this bubble of space that actually has lower density than other parts of the Milky Way, caused by hundreds of supernovae going off and blowing away a lot of this material. And yet, obviously, we know we have life here. So are those the kinds of things that you could say, oh, you need to have these regions that have been cleared out by supernova? Or, I can sort of imagine things that could change our perspective on searching for life on other worlds.
So for that study that we are doing, and I think also for the, at least next 50 years of astrobiology where we explore our neighborhood, we just start with the assumption that our neighborhood is somehow representative, or at least, we keep in mind that whatever we derive may not be, expendable to the whole universe. But there's even biases before that. So even if if I do a survey with my telescope and I find, 50 candidate Earth twins, however I define them, there might still be a couple of super Earths that somehow sneaked in, or maybe some, rocky margins that for some reason I underestimated or overestimated the temperature. So my sample that I then start to characterize and search for life might already have a bias in it. And then I try to derive the number of, or the fraction of Earth-like planets who have life, but I already have a couple of Mars-likes and Venus-likes in my sample, which I didn't know. So this is another bias that we actually included in our calculation. So that also means that before we start characterizing, we already should know quite well which kind of planets we look at, right? So because then we derive a fraction of a very uneven sample, and then this number also becomes not really informative.
And so, like what I'm hearing is percentages multiplied by percentages informed by Bayesian statistics. And, as you look out further and further and you keep updating your priors, when would you, as a person who is excited about the possibility of finding life on another world, start to go, we might be alone?
It's a good question. I think if we do the survey with HWO or live, and we look at dozens, maybe in the order of 50 Earth similar planets, maybe even planets around M stars and at inhabitable zone of M stars, and we won't find this combination of oxygen and methane, for example, then I would be pretty confident that life as it is at the moment on Earth is pretty rare. And then it goes to the next step and see what could be other biotopes and what could be other anomalies. So I'm pretty sure there's going to be a lot of discussion. We already have discussion with the very first James Webb spectra now. So I think we won't have a lack of potential biosignatures, at least for a while. We don't have. We have them already now, but I think if we get this up, and this is kind of like one of the take home messages from the paper. So if we do this survey in a size of 30 to 50 planets, then we have a sample that is good enough to at least make some deductions about the frequency of life and habitability in the universe. So this is where we are coming from. Right? We're designing these missions right now, and we want to make sure that if we don't find anything, we still learn something.
But that idea of like 50, let's say there's some future beautiful version of a space telescope that is able to directly observe the atmosphere of a Earth-sized world orbiting around a sun-like star within the habitable zone, like another Earth. And we look at 50 of them, and none of them have any of the signs of whatever is the biosignatures that people have developed at this point. How was sort of like, how does that then scale to the larger universe? Is it, is it 99% empty? Is it 99.9? Like, just give people a sense of
Mhm.
how unpopulated the universe might be.
So if you use this framework that we derived, or this Bayesian statistics, which it is essentially, and you put this 50 in and you're 100% sure, then we are 99.9% sure that the upper limit is lower than 10%. So that means after that observation, we can pretty confidently say the fraction of Earth-like planets that have life is smaller than 10%. But that's still a lot, right? So we still have billions of planets, and 10% of them is still 100 million. So that doesn't mean that there's no life at all, but it means at least, the optimists in our community might have to, reevaluate their models, and the pessimists could maybe, go on a victory lap for a bit, so I think it won't exclude. I mean, as you said in the beginning, right? You can always search for the needle in the haystack, but you can never exclude that there's a haystack in the needle, that there's a needle in the haystack, right? Because it's there's no way that you can check every planet individually, but we get a pretty good idea about the statistics. Similar actually to the Kepler telescope, which looked at a bunch of stars and then was able to derive the fraction of stars that have um, that have planets like Earth. And then with the next step, we can look which fraction of these planets do have signs or do not have signs of life. Yeah.
Yeah. And I wonder though, I mean, I've sort of held this position for quite a while that the universe appears to look like wilderness, that it appears to look like there's nobody is doing anything at a grand scale that is obvious to our eye. People aren't rearranging galaxies, and people aren't enclosing stars in Dyson swarms and stuff. That it looks like it's just raw material out there as far as the eye can see, untouched wilderness, in a way that's very different from the way Earth looks. Um, but that runs counter to what is this sort of emotional, almost faith that there must be life in the universe. How can this be that we're here? How can we be the only one? How arrogant to think that we are the only life. So when you sort of put on your philosophy hat and think about the consequences, back to Arthur C. Clarke's original statement, I would love to sort of hear your thoughts on, if alone versus not alone.
So my solution, my favorite solution for the Fermi paradox. So, yeah. Yeah, I agree. It would be a pretty lousy universe if we were the best it could create, right? So I mean, there's as many there's probably 50 or more potential solution to this Fermi paradox that you brought up, right? So where is everyone? And you know, one of the ones that I like is actually that the difference between civilizations might be so huge that it's not within our perception to even see it. Like the dark matter could be a product of some just super intelligent. It's like this saying, like some every advanced technology cannot be distinguished from magic or something like
I
this,
think that's
right?
another Arthur C.
And
Clarke quote.
yeah, and then every super advanced civilization might not be distinguishable from nature for us, because they change stuff on such grand scales that it becomes one with nature for us, because it's so unperceptible for us. So this is one solution that I find pretty intriguing to think about. Not saying that this is what I think is the solution for it. So and there's actually also work, I think, by Dave Kipping once wrote the paper that if two civilizations meet, they are not like 50 years apart, like in Star Trek, where they just got warp drive 50 years ago, and we are 50 years later. It's probably like eons or thousands of generations different. And if you think about this, that might be good. And then there's always this rareness, right? I mean, there's so many coincidences that led to intelligent life like ours, that it might not just be also not necessarily an evolutionary pressure to get more intelligent. We still have to prove that our intelligence is not just an accident, right? So we might have developed this intelligence and destroy our habitat with it, and it might not even be, evolutionary an advantage to be so smart as we are, right? So there's really so many explanations and potential explanations. But what I like about it is that if you think about it, it's a lot of reflection about ourselves. I think this is what is really the cool thing about technosignatures and SETI and thinking about the Fermi paradox, that you reflect about yourself as human, about us as a society, right? So these all these thoughts, are we actually worth it, and how are we treating our environment? If we were the aliens coming somewhere else, how would we? So it's much more reflecting on yourself than, or it's as much as reflecting on ourselves than it is imagining how the others are. And this is what makes this whole thought so intriguing for me.
Yeah. I mean, I think where it becomes practical for me is I sort of think of an analogy as like you're in a family and you're an only child versus someone with siblings. And so if you're the only child and your parents are aging and you're going to have to start thinking about how you're going to be able to help them out with their long-term issues, it's all on you, and you know that this is going to be your responsibility and that they're going to be relying on you to help them with supporting them as they get older, which is my situation. But if you have siblings, especially if you have a lot of siblings, then that load is shared. Then you know that you're not alone in taking care of the parents, that you can sort of work with your siblings, and you can come to some kind of agreement, and someone can live close to them, and someone else can support them monetarily, whatever it's going to be. Which is the lesson that I'm going to be telling my children. But because I have more than one, but that as we think about how we consider our planet, that if we are completely alone in this universe, then there's no second chance. We've got to take good care of our planet. We've got to make sure that we can sustain humanity and hopefully carry this light of consciousness out into the cosmos. But if we realize that we're just one member of an enormous galactic federation and they're all around us, waiting for us to develop warp drive before we can finally join the Federation, then that's a totally different future path for the humanity takes. It's not about, although obviously the being good to the planet and so on, they're the same goal, but still sort of how we perceive our place in this universe is very different.
No, I totally agree. I mean, this is what I meant, right? It's a lot reflection about ourselves. Are we alone, and then, you know, are we maybe even a failed species? Maybe are we slowly but surely getting to this point that we might just be an evolutionary accident and should, for the sake of the planet, just go away? Or are we, on the other hand, just hoping that magically this alien spaceship arrives and solves all our problems, right? So this is exactly this reflection on ourselves, and I hope, by doing these philosophical probably exercises, it might help, to reflect on ourselves and find, our place in the universe, no matter if we find something or not, right?
When do you think, like, if people want to put in their calendar when they will get this answer, when someone will go back to your paper and take the math and run it based on the number of known exoplanets that have been found and come up with that greater than 10%, less than 10% number, as you sort of think about the future, when should I set my calendar alarm for?
I mean, what we see right now, this might be just, I'm pretty sure it's going to be it's sort of like an incremental detection, right? There might be, as we heard, just a couple of, just last week, there might be the first barely detection of something that might be in certain context a biosignature, and then eventually it's a more significant detection, but it's not sure if it's a biosignature, and then we find a second planet with a similar, and so it's going to be incremental, a bit like water on Mars. First it was just water in some brines, and then it was water in some underground lakes, and then it was a whole ocean 4.5 billion years ago or something like this. So I think it's going to be an incremental process. So it's not like this big, unless there's this big techno signature we suddenly find out of nothing. It's going to be, as it often was in in astronomy and most of science, it's always going to be an incremental, and this might be actually hard to communicate with the public, I have to admit, and we have to be careful and maybe stick together as a community to really make sure we communicate this in the right way. But I think this is going to be incremental. I think it's starting now. I mean, we are right at the time where we see the very first hints and where we realize we have the technology to find it if it's there. So I don't think we have to wait very long to. I mean, we're already discussing about it right now, but to get to finish, to really to get this systematically, to really scan our whole neighborhood, we have to wait for the next generation of telescopes. So we might be lucky with a few shots with James Webb, but we need HWO or LIFE to really be systematic about it.
Yeah, I mean, the next big tool in the toolkit will be the extremely large telescope, which is 3 years away, 2 years away. That's quick, and it should be able to do this to some degree. If that doesn't get us the answer that if life is everywhere, hopefully the extremely large telescope will give us some kind of interesting signal. But as you say, then if that doesn't work, then the Habitable Worlds or the Life telescope that you're involved in, those will. Are they the ones that will give us the number, do you think? Either of those two telescopes?
At least we are building them right now to get the numbers right. And this is exactly where this study that we just published came from, to really see what number. And also, if you want to answer different questions, there's some grad students in our group also working on this. So we need to figure out what is a good sample for a survey like this, to really not just be lucky and not just go on a fishing expedition, but really to get some statistical numbers that help us to understand the theory of life better. So, and this is where we are coming from. So right now with James Webb and also with the ELT, we might get punctual observations and can sample the best targets in a really biased way because we just can observe what's best for us. But with this next generation mission, we really try to build a statistical mission, so to speak, not just a fishing expedition in quotation marks. Not to push down on the other missions, but it's really a different approach, right? One is really to do statistics like comparative exobiology, and the other one is really just to get these few targets, best targets, analyzed as good as possible.
And assuming that the funding ramps up beautifully for both telescopes, and both Europe and the United States are 100% on board with building these wonderful next generation telescopes, when could we see first light?
So I would be bold and say with unlimited funds, which is obviously unrealistic. It probably could be pushed in 5 to 10 years. So I think the technology it's not ready, but it's on levels where if you invest and have unlimited funds, it could be ready in 10 years, let's say. And then, realistically, so we are realistically / optimistically, internally talking about launch 2040, which is mostly driven by my retirement date. But so I think within the next 2 decades, we will see it. Funding, assuming we get funding from whatever source. Yeah.
Daniel, the question I always ask: what are you obsessed with right now?
Honestly, with what I'm doing next. So, as I mentioned before, so the main work of building up the science case and developing the community for life is done now, which was my main task. So I'm actually at least taking a break from life in an official role for a bit. So so I have a lot of free bandwidth in the future. So I'm obsessed with many things like designing my own board game and expanding some professional development courses that I'm giving, or building my own mission to the moon. So I have plenty of technosignatures. So this whole SETI and search for extraterrestrial intelligence, which was more of a fun side project of mine, might become a bit more of a focus for me. So that's what I'm obsessed with at the moment. So what I'm doing next with my free time.
Yeah, that idea of technosignatures. I mean, this for me has been quite exciting. That for the longest time, it was there was the giggle factor at people saying, well, we want to search for life in the cosmos. But now you've got NASA organizing conferences where people are talking about this, and very serious astronomers are talking about this, and nobody's giggling. Everybody is sternly nodding when they think about detecting the presence of nuclear wars on other planets and chlorofluorocarbons in the atmospheres of other worlds. You know, and yet we're really scratching the surface for what is possible out there. And sort of, how do you think about us searching for technosignatures?
So, I mean, obviously, since I'm part of this community and have my own few of my own techno-signature projects, I'm obviously, a fan of it. So, as I mentioned before, first of all, because of this whole self-reflection stuff, even if we don't find aliens, we just reflect on ourselves, learn about, the human condition, if you want, right? But then also, then next, motivated by all these developments or all these stuff that we learned about exoplanets recently, right? So 10 years ago, we weren't sure if there weren't, or maybe 20 years ago, we weren't sure that there were exoplanets. After Kepler, we know, the frequency of Earth-like planets is 10%. And then that gave us more arguments to let's think about this. And then we also built these telescopes in the future. And then also statistically it might be intelligent life might be much rarer than microbial life, but the signals might be higher. So if you know so a planet full of microbes might only have like a tiny signature of oxygen and methane in the atmosphere, whereas a technological civilization might be less abundant but has a really strong CFC signal in it. So it's a bit about your own biases. Do you assume there's much of it? But I don't think the chance is not zero. And it's again like if you find something, it might be one of the biggest things ever found in the history of science. So this is also a driver. And then also, as always, you always find other interesting things. So I'm maybe it's a bit far reach, but I'm doing another project where we look for anomalies on the moon. So we essentially run an AI to find anomalies on the moon. And the first idea was we find Apollo landing sites and all sorts of crashed UFOs and whatnot. But then we suddenly started to find fresh impacts and cave pits and irregular marrow pitches. So all these things that are also interesting in other scientific. So even if your main motivation is to look for aliens or to search for radio signals, you still find radio signals of interesting pulsars, or you find patterns on the moon that might not be UFOs but something else that's interesting, right? So I think this is a lot of motivation to also do the SETI and techno-signature work. Yeah.
Yeah, I mean that's one that I'm really excited about, is that if you follow the sort of thought experiment that an advanced civilization is going to create self-replicating robot probes, the von Neumann probes, and they're going to send them off into the cosmos, and they're going to go from star system to star system and set up shop and dismantle asteroid belts and build more probes and continue on this exploration, then they're going to leave debris behind, and you would go to the places and look very carefully where you're most likely to see that debris. And you don't have to look to a different star system. You just have to look here in the solar system. And so the moon is a great place. We can see the moon. We can examine its surface and look for anything that's a little weird. Yep. But also there's countless asteroids in the solar system and Oort cloud objects and so on and so forth. And we've barely scratched the surface on what we've explored.
Yeah. And similar to what we discussed about life or the search for biosignatures, we are just getting to a stage where we have the technology. Now we have AI models that can scan the whole lunar surface. Now we have rovers that can bring samples back and stuff like this, right? So this is also part that drives this. So now we have so far we could only speculate if that scenario from this science fiction would be real, from this science fiction story would be real, what would be observed. But now we actually can observe it, right? And this also helped making this shift and make it a more mainstream thing to think about techno-signatures nowadays.
Yeah. And like up until this point, the only people who've been like scanning the surface to this level of detail is people who are looking for, the pyramids on Mars and the face on Mars and things like that. And having periodelia effect.
Pareidolia, yeah.
Pareidolia, yeah. And now actually the AI is perfectly trained to know what's a rock and what's a ancient von Neumann factory, and we may get to this point where we can conclusively say there are no von Neumann factories on the surface of the moon. Under the moon, that's a totally different story, but that's, well, Daniel, absolute pleasure to talk to you as always. Thank you so much, and definitely keep me posted as you work on some of these additional challenges.
Will do.
I hope you enjoyed that conversation with Daniel Angerhausen. Now, I've got a larger version of this interview over on Patreon, Interview Plus. And in this, we do an update on the Large Interferometer for Exoplanets. It's been 2 years since I interviewed Daniel, and a lot of really interesting new work has been done. Progress has been made on the kinds of discoveries that could be made with this telescope, as well as starting to work with the various people who could greenlight it and turn it into an actual mission. So if you want to learn what is the state of the cutting edge exoplanet hunting telescopes, you're going to want to listen to this additional interview. And again, that is available completely for free over on Patreon. You don't need to sign up to anything. You can just click a link in the show notes and go over there and watch that longer version of the video. Now, I'm going to give you some final thoughts and some further references, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew Gross, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nelson, David Giltona, David Matz, Dustin Cable, Evan Perot, Greg Feely, Hen Schultz, Hudson Ward, Jay Graves, James Clark, Jeremy Maddern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Modzo, Paul Robach, Ren Kaidu, Robeck, Sean Sargent, Stephen Fowler Munley, Vlad Shiplin, and Wolfgang Klotz, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. Obviously, this is a topic that I am incredibly excited about, and I know that you are as well. And yet it feels like it's going to take forever. Like, we just got access to James Webb, and now you're telling me that James Webb can't find life on other worlds? Yeah, unfortunately. We're about to have the extremely large telescope come online, and it's going to have a hard time finding life on other worlds. Yeah, unfortunately, that we need those next generation telescopes. And so if you're familiar with LUVOIR, LUVOIR has been turned into the Habitable Worlds Observatory, and yet, we're now wondering what's going to happen with the funding for NASA, whether or not this observatory will ever move forward. And yet there are other plans, and so we've got the exciting possibility of a global community of astronomers and space agencies coming together to build this next generation of space observatory. And hopefully, in our lifetimes, by the 2040s, humanity will have taken its best possible chance at finding out the answer to this question. Now, I've got so many interviews about these kinds of next generation telescopes, as well as my last interview with Daniel Angerhausen, where we talk about the LIFE telescope in specific, but also a really fascinating interview with Lee Feinberg, who is working on the design for the Habitable Worlds Observatory. So if you want to sort of see other interviews in this subject, I've got lots and lots that you can explore. All right, we'll see you next time.